Okay, so let's do one more example. And this one is, I think, the most difficult and involved one that we're going to do, uh, but I think it's kind of interesting. So let's say you're at the beach with your dog. There's your dog, and you're playing catch with this ball. And you're standing at the shore, and you throw a ball into the water for your dog to catch. Now, from where your dog is standing, the ball is 20 feet down the shore, right along the shore, so the dog can run on the sand, these 20 feet. And then it's 12 feet deep into the water, rather 12 feet away from the shore. Okay, so if your dog can run 13 feet per second and swim 5 feet per second, then what path minimizes the time it takes your dog to get the ball? Now, the fact is that, what's going on here, first of all, I'll just give us some information. I'm drawing the picture for us, and also I'm just going to tell us that the dog is going to take this sort of path. He's going to run along the shore until some point where he decides it's worth his while to cut into the water and start swimming. And then he's going to swim to the ball. It doesn't make sense for him to run all the way down the shore and then, till he's perpendicular to the ball and then to swim across to the ball. He'll save some time by cutting into the water earlier, but it doesn't make sense for him to just jump straight into the water because he can run a lot faster on the sand. In fact, I think experimentally people have done problems like this to, actually recreated this in real life to see how well a dog follows a path, the correct path, and apparently, not that dogs can do calculus, but creatures are built so that they naturally solve these sorts of minimization problems with some degree of accuracy. But anyway, so what path is going to minimize the amount of time it takes the dog to get to the ball? That's what we're going to figure out. We're going to see how long does he have to run along this line, and then when should he cut in and swim along this line to get to the ball in the shortest amount of time. So the picture is given to us. Great. What do we know? We know the distance along the shore, that they're 20 feet along the shore. We know the distance from the shore to the ball, which is 12 feet. And we also know how fast your dog can run on the sand and how fast he can swim in the water. What we don't know is how long your dog should run along the sand, which we're going to call x. So x is going to be this distance right here from where your dog is to where he decides to jump in the water. Then y is going to be this distance right here, which is the distance from when he jumps into the water to getting to the ball. We also don't know the time that it's going to take your dog, but that's what we want to minimize. So that's going to be the quantity we're optimizing. The amount of time it takes your dog to get to the ball, we try to minimize it. Okay, so I've taken our diagram and I've sort of simplified it some here. We have 20 is the distance along the shore, 12 is the distance from the shore to the ball, x is how far the dog runs, y is how far the dog swims. Let's notice that y and 12 form two legs of a right triangle. The third leg right here, it has the length 20 minus x because it is x less than 20. Okay, let's start coming up with equations. So first of all, we need some sort of equation for the time that the dog takes to run. Well, we know a relationship between time and distance, namely distance is speed times time. If I solve that for t, I get t, time, is equal to distance divided by speed. So this will allow me to get the two components of the dog's time getting to the ball. There's the time running, which is x feet divided by 13 feet per second, and then the time swimming, which is y feet divided by 5 feet per second. So altogether, the amount of time that the dog is running is t equal to x divided by 13 plus y divided by 5. Next, let's look at this right triangle here that has the legs y, 12, and 20 minus x. So the Pythagorean theorem says that 20 minus x squared plus 12 squared is equal to y squared. Great, fantastic. And I've just multiplied this out to get x squared minus 40x plus 544 is equal to y squared. Okay. Now we have two equations and we have three unknowns. Great. That should be good enough. So let's solve this equation right here for y. Why solve it for y and not for x? Because it looks just easier to solve this for y just by taking the square root. And I'll plug that into the formula for t. So y is the square root of x squared minus 40x plus 544. And so t is equal to x divided by 13 plus the square root of x squared minus 40x plus 544 divided by 5. Finally, what is the domain for x? Well, this is really coming from the problem. Nothing about this equation really says that x can't be really far negative or really far positive. I suppose if x were really big negative, this might actually end up being a negative time, which doesn't make any sense. I don't know if that happens. But in any case, where did I get this domain from 0 to 20? Well, the dog can either just immediately jump into the water and go to the ball, which would be x equal to 0, or the dog can run the 20 feet down the shore and then to the ball. It would not make sense for the dog to run backwards and then jump in the water. It wouldn't make sense for the dog to run beyond the ball and then jump back and swim back towards the water. It only makes sense for the dog to run between 0 and 20 feet along the water. Okay, so let's optimize by taking the derivative of t and setting it equal to 0. Now, I would just like you to check. Make sure that I didn't mess up. The derivative of t with respect to x is 1 over 13. I'm sure you can see that fairly quickly, but plus x minus 20 over 5 times the square root of x squared minus 40x plus 544. Make sure that that's the right thing, and then I didn't mess up. Anyways, that's equal to 0, so we solve. I'll subtract 1 over 13 from both sides. This feels a little weird to me because on the left side I have something which could be positive, I don't know, but on the right side it's negative. Does it make sense for this to be negative? Yes, because x is less than 20, so the numerator is negative, the bottom is positive, so negative over positive is negative. Fine. Great. Now I'm going to cross multiply. I got 13 times x minus 20 is equal to negative 5 times the square root of x squared minus 40x plus 544. To solve this, I'm going to have to square both sides. On the left side I get 169 times x minus 20 squared. On the right side I have 25 times x squared minus 40x plus 544. And I distribute and I square out on the left-hand side to get 169x squared minus 6,760x plus 67,600 equal to 25x squared minus 1,000x plus 13,600. Whew! Okay, this is a lot of work, but let's keep going. So, okay, this is a quadratic equation, and I'm going to use the quadratic formula to solve this because things are pretty big. So I'm going to subtract this over to the left-hand side. I get 144x squared minus 5,760x plus 54,000 equal to 0. Now, I've set things up nicely here so that actually 144 divides all of these coefficients. So when I do that, I get x squared minus 40x plus 375 equal to 0. So I plug this into the quadratic formula. I get 40 plus or minus the square root of 1600 minus 1500 over 2. That's b squared minus 4ac. That gives me 40 plus or minus the square root of 100 over 2, which is 40 plus or minus 10 over 2, which gives me the values of 15 and 25. Now, I've already said that our domain for x is between 0 and 20, so 25 is out. But you can also check fairly quickly that 25 doesn't make sense here. Why? Because if I plug it back into this original expression for t prime, I get 1/13 plus 25 minus 20, which is 5, over 5 times the square root of something. And whatever the square root is, if it's defined, it's positive. So 1/13 plus something that's positive equal to 0? No, that's not right. So in fact, 25 is no good, and the only place where this function has derivative 15 or 0 is at 15. Okay, so we still have to go ahead and check that this is indeed the minimum. We have two different ways we can use this first derivative test, or we can go ahead and just plug it into, since we have closed interval on a continuous function, we could just do the closed interval method. So if the dog runs no feet along the shore, which means that he jumps straight into the water and swims the whole way, it takes him 4.66 seconds. If he runs 20 feet along the shore and then swims the 12 feet to the ball, it takes him a shorter amount of time, which is 3.94 seconds, because he can run a lot faster than he can swim. However, if he optimizes and runs 15 feet along the shore, and then jumps into the water and swims, it takes him only 3.75 seconds. Look, it shaves a quarter of a second of getting to that precious ball. Fantastic. So that's what your dog is going to do. So, what is our conclusion? The time is minimized at about 3.75 seconds. When the dog runs 15 feet along the shore and then swims, you can check that it's 13 feet in the water. There's your dog. Nice.